Hello, this is the Section 8.2 lesson. Section 8.2 is somewhat lengthy, but the rest of the sections for the rest of the semester are all relatively short. For this lesson, you'll need to print figure A87 on page 403. Figure 8.7 is a flow chart that we will be using frequently throughout the rest of the semester. You will also need table A2, which is your z-score table. Most of all of the topics that we're going to be talking about for the rest of the semester would fall into the category of inferential statistics. To refresh our memory, inferential statistics are concepts where we use information from a sample to make a conclusion about a population. Now remember, the population is the set of all elements that we're interested in a particular scenario. A population can be a group of people, but it doesn't necessarily have to be. A sample is a portion of that entire population. It may be a very small portion, like 2 or 3 or 5 or 10. It may be large, like several hundred or several thousand, but it's only a portion of the entire population. We mentioned back in chapter 1 that the difference between a sample and a population is what statistics is really all about. We really want to know something about the entire population, but that's very difficult, if not impossible, to determine, because it would require us to get information from every single member of the population. So instead, we get information from every member of a sample, we calculate sample statistics, and we use those statistics to make some conclusion about a population. So as our first example, what's the best way to find a job after you graduate? There are a lot of different ways that you could find a job. You could look in newspapers, you could go to the internet, you could look at job placement services, or another popular way is what's called networking, and that's where you know somebody who knows somebody who knows of a job. So you find your job through a social network of some sort. Well, a career counselor claims that most workers find their jobs through networking. Is this claim true? You may have heard a claim something to that effect before. We want to test if that claim is true. Do most workers really find their jobs through networking? Okay. Well, to begin to analyze that, in a recent survey of 703 randomly selected workers, 61% said they found their job through networking. Now we might be tempted to stop right there and say, well, that proves the claim, because 61% is greater than half. Proves the claim. Well, we've got to be very careful about understanding what this statistic of 61% shows and what it does not show. What this shows is that in this sample, most found their jobs through networking. This is only a sample of all workers. The claim is made about the population of workers. So what we need to determine is, does it support the claim that in the population of workers, most found their jobs through networking? Again, the claim was made about the entire population of workers. Our data here comes from just a sample. Our sample data does appear to support the claim, but just how strong is that support? Is it very strong support that we could use it to conclude that the claim really is true, or is it just very weak support that doesn't give much support at all? Well, to determine this, we're going to use a process called hypothesis testing, which is a formal approach for determining if data from a sample supports a claim about a population. And there are 4 basic steps in hypothesis testing. First, we state the claim in the form of what we call hypotheses, and there's going to be 2 of them. Second, we calculate what we call a test statistic. Third, we calculate a p-value. P there stands for probability. And then fourth, we state the final conclusion. So let's talk about these hypotheses. The null hypothesis, denoted by h sub 0, is a statement that the value of a population parameter, such as a proportion, mean, or standard deviation, is equal to some claimed value. Now here are 3 examples of 3 different null hypotheses. One null hypothesis could be the statement that p, a population proportion, equals 0.5. That's one possible null hypothesis. Another null hypothesis could be the statement that mu, a population mean, equals 98.6. A third null hypothesis could be the statement that sigma, a population standard deviation, equals 15. Now notice what these all have in common is that they all have an equal sign. It's all of the form are parameter equals some number. A null hypothesis will always have an equal sign, like these three examples. The second type of hypothesis is called the alternative hypothesis, denoted by H sub 1, and it's the statement that the parameter has a value that somehow differs from the null hypothesis. So here are three examples of null hypothesis that would correspond to the three examples of the alternative hypotheses on the previous slide. So our first null alternative hypothesis could be the statement that P, our population proportion, is greater than 0.5. Our second alternative hypothesis could be the statement that mu, our population mean, is less than 98.6. Our third alternative hypothesis could be the statement that sigma, our population standard deviation, does not equal 15. So note what these have in common. First of all, they all have a population parameter, either p, mu, or sigma. Second, none of them has an equal sign. Alternative hypothesis will never have an equal sign. Could have a greater than sign, a not equal to sign, or less than sign, but it will never have an equal sign. Okay. So let's go back to this first claim, and we're going to set up our null and alternative hypotheses. So first thing I've done here is restated our claim in slightly different terms. The claim is that the proportion of workers who get their jobs through networking is greater than 0.5. Now again, this is equivalent to the original claim, just stated in a slightly different terms. The original claim was that more than half. Well, more than half means that the population proportion is greater than 0.5. And so I've just restated the claim here in terms of proportions. The proportion is greater than 0.5. Okay. Now the first thing we're going to do when we begin to set up our null alternative hypotheses is to define the parameter. Now this is a step that the book doesn't do, but I do because I think it's important. When we define the parameter, we simply state what it is we're making a claim about. We're not simply restating the claim, we're just stating what it is we're making a claim about. So in this case, we're making a claim about the proportion of all workers who get their jobs through networking. So our parameter is P. It equals the proportion of all workers who get their jobs through networking. And we stress the word all there because we are making a claim about the population of all workers, not just the 703 that appear in our sample. So after we define the parameter, we're going to go through a four-step process for setting up the hypotheses. And I recommend that you go through this four-step process on every single hypothesis test problem we have. It'll simplify things in the end. It may seem like more work than necessary, but it's going to help keep things organized. The first step is to state the claim in mathematical notation. Now in mathematical notation, the claim is simply P is greater than 0.5. Second, we state if the claim is false. Well, the opposite of greater than 0.5 is less than or equal to 0.5. So if the claim is false, then P is less than or equal to 0.5. Now our null hypothesis is going to come from the one of these two statements that contains equality. The second one contains equality, so our null hypothesis is the statement that P equals 0.5. Now it's not the same as that second statement, but it comes from the second statement. Again, remember the null hypothesis always has an equal sign. Now our alternative hypothesis is going to be the other statement. So alternative in this case is the statement that P is greater than 0.5, which is the same as the original claim. Now in not every hypothesis test will the alternative hypothesis be the same as the original claim. In some it will, but in most it won't. Okay, let's look at another example of setting up our null and alternative hypotheses. Here's a claim. The mean weight of airline passengers with carry-on baggage is at most 195. So when we have a claim like this, the first thing we have to determine is if we're making a claim about a proportion, a mean, or a standard deviation. In some cases it's rather obvious, in other cases it's not as obvious. Right here it says the mean, so that means that our parameter is mu. We're making a claim about a population mean, and the mean we're making a claim about is the mean weight of all airline passengers with carry-on baggage. And again, we stress the word all there because it's a claim about the population of all airline passengers, not just a few in a sample. There's our parameter. Now our claim in mathematical notation is that mu is less than or equal to 195, because at most means it less than 195 or could be equal. Well, if false, then mu is greater than 195. The opposite of less than or equal to 195 is greater than 195. Again, the null will come from the one of these two statements that contains equality. So it's going to be the first statement, mu equals 195. The alternative will be the other statement, mu is greater than 195. So I've got a third example of setting up null and alternative hypotheses. The claim is that the standard deviation of IQ scores of actors is equal to 15. Now in this case we're making a claim about standard deviation, so our parameter is going to be sigma. It's the standard deviation of IQ scores of all actors. Again, we stress the word all there because it's a claim about the population of all actors, not just a few in a sample. So the claim is that mu equals 15. So if false, then mu is not equal to 15. The null comes from the one of those two that contains equality. It comes from the claim, sigma equals 15. Now in this case, it's the same as the original claim. And the alternative is the other statement, sigma is not equal to 15. Okay. Now let's go back to this original example of a claim about the proportion of workers. So here's our claim. The null hypothesis was p equals 0.5. The alternative is that p is greater than 0.5. Well, in our survey, we saw that 61% found their jobs through networking. So our sample proportion, p hat, is 0.61. That number is what we call our sample statistic because it comes from the sample. Well, let's make an observation here. This sample proportion of 0.61 appears to be unusually large if the null hypothesis is true. When we do our calculations, we're going to do them based on the assumption that the null hypothesis is true. So if the population proportion really is 0.5, then it would be unusual to get a sample proportion greater than 0.5. So we need to determine, is this an unusually large proportion? If it is, then there's maybe something wrong with our assumption. If it's not an unusually large sample proportion, then maybe there's nothing wrong with our null hypothesis, our assumption. So to determine if it's unusually large or not, we're going to use this rare event rule, which informally says that a number is unusually large if the probability of it or more is less than 0.05. So we need to determine the probability that p hat is greater than 0.61. And again, we're going to do our calculations assuming that the null hypothesis is true. So we're first going to convert that sample statistic over to a z-score. Now in the next section we're going to talk about how this is done, but in this case z is simply equal to 5.83. This number is what we call the test statistic. Okay. So now the probability that p hat is greater than 0.61 equals the probability that z is greater than 5.83. So we've converted this over to a standard normal distribution problem, and we know how to calculate that probability. Okay. So I draw my standard normal bell curve, go to z equals 5.83. I shade to the right because I need to know the probability that z is greater than 5.83, and that area is the probability I want. Now we can look that up from our table. The area to the left of z equals 5.83 is 0.9999, so we'll take the area to be 0.0001. It's actually much smaller than that, but that's our probability. Now this probability is given a special name. It's called a p-value. And in this case, the p-value is the area underneath the bell curve to the right of the test statistic. And again, the p-value is a probability. In this case, it's the area to the right of our test statistic. Now informally, this p-value is the probability that the sample statistic occurred by chance, assuming that the null hypothesis is true. So our p-value here is very small. So that means that what we observed is highly unlikely, assuming the null hypothesis is true. So that's an indication that maybe our null hypothesis isn't indeed true. Okay. So next we need to interpret the p-value. And so we'll choose a confidence level. Now the default value for confidence level is always 95%. If no confidence level is given, then we'll take it to be 95%. And so that means our associated value of alpha is 0.05. Alpha is what we call the significance level. Now our criteria for interpreting the p-value is this. We say we reject the null hypothesis if the p-value is less than or equal to alpha, and we do not reject the null hypothesis if the p-value is greater than alpha. So in this case, the p-value is very small, which is definitely less than 0.05, and so we would say we reject the null hypothesis. Now this statement is what we call the technical conclusion. It's a conclusion, but it's technical because we're using this term null hypothesis, and a layman isn't going to know what we're talking about when we say null hypothesis. Now our last step is to word the final conclusion. And this flowchart here is figure 8.7 from your book. Now this one is a little bit different than what's in your book. It looks a little different, but the substance is the same. We're going to use this flowchart to word our final conclusion, and we're going to see this flowchart many times throughout the rest of the semester. We're going to get really sick of looking at it, but luckily it's easy to use. So we start up in the upper left-hand corner with this diamond. Does the original claim contain the condition of equality? In this case, the answer is no, because the claim is that p is greater than 0.5. So we follow that red arrow down. Next we go to this diamond. Do you reject the null hypothesis? And our answer is yes. And so we word our final conclusion starting in this way. The sample data support the claim that, and then we simply state our original claim. So here our final non-technical conclusion. The sample data support the claim that the proportion of workers who get jobs through networking is greater than 0.5. Now that conclusion is a little bit wordy, but that's just the way statistical conclusions are. They're often very wordy. So our sample data did appear to support the claim, and we concluded through our hypothesis test that support was strong enough to indeed say that the sample data supports the claim. Now some quick terminology here. The p-value is the area under the bell curve to the right of the test statistic, and so we call this a right-tailed test. In a bit we'll see a left-tailed test as well. Next example, here's a claim. We're going to set up our hypotheses and do a formal hypothesis test. So a statistics professor claims that less than half of all statistics students pass Introduction to Statistics. So let's test this claim. Let's set up our hypotheses. First we define our parameter. Now the word proportion is not used in our claim. However, it says less than half. Half means 50%. Percent indicates proportion. So our parameter is p, the proportion of all stat students who pass Introduction to Statistics. And again, we use the word all there because we're making a claim about the population, not just the sample. So the claim in mathematical notation is that p is less than 0.5. If false, then p is greater than or equal to 0.5. The null hypothesis comes from the one of those two that contains equality. So it comes from the second one, statement that p equals 0.5. The alternative is the other statement, p is less than 0.5. Okay, so we started testing this claim that less than half of all statistics students pass Introduction to Statistics. Here's some data. A survey of 321 statistics students from across the nation shows that 44% pass Introduction to Statistics. So our sample statistic p hat here is 0.44. Now as before, we might be tempted to stop here and just say, well, this proves the claim because 44% is less than half. But again, what this proves is that in this sample, less than half. Our claim is about the population of all statistics students. We need to determine just how strongly this this sample data supports our claim. Okay. So if we convert that over a test statistic, it equals negative 2.15. Again, we'll see how this is done in next section. Now in this case, our p-value is the area under the bell curve to the left of the test statistic. Now why is it to the left? Well, it's because our alternative hypothesis is that p is less than 0.5. That less than sign kind of points to the left. That indicates the p-value is the area to the left. So our test statistic negative 2.15. I look on my, my table A2 for the area to the left, and that's 0.015. So that is my p-value. We call this a left tail test because the p-value is the area under the left tail of our bell curve. Now we'll interpret this in the same way. We'll choose a confidence level. Here we'll choose 99%. So alpha is 0.01. Again, we use the same criteria. We reject the null hypothesis if the p-value is less than alpha. We do not reject it if it's greater than alpha. Our p-value of 0.015 is just a little bit greater than alpha, and so we do not reject the null hypothesis in this case. Now we'll word it in the same way. The original claim did not contain equality, so we go down the red arrow. Do you reject the null hypothesis? No, we do not. So there is not sufficient sample evidence to support the claim that less than half of all statistics students pass Introduction to Statistics. Okay. So our sample data did appear to support the claim, but that level of support was just not great enough. So we conclude that it does not support the claim. So I got a next example of a hypothesis test. Mars Inc., the manufacturer of M&Ms, claims that 10% of M&Ms are blue. Okay. Now first thing we need to do is find our parameter. In this case it's a proportion. Again, the word proportion is not used in the claim. However, we saw 10% there. 10% implies proportion, so it's a proportion. In this case, p is the proportion of all M&Ms that are blue. Again, we stress the word all there because we're making a claim about the entire population of M&Ms, not just the few in a sample. So now our claim in mathematical notation is that p equals 0.10. If false, then p is not equal to 0.10. The null comes from the claim. It's the statement that p equals 0.10. And the alternative is the other statement. P is not equal to 0.10. Okay. Now, we'll go out and get some data. In a random sample of 50 plain M&M candies, none was blue. So our sample proportion here would be 0. 0 divided by 50 is 0. Again, this doesn't prove our claim or disprove our claim. At first glance, it may seem to disprove it because 0% is a lot smaller than 10%. But again, this comes from a sample, not from the entire population. So we convert that over a test statistic. In this case, it's negative 2.36. Now in this case, our p-value is twice the quote-unquote extreme region bounded by the test statistic. It's the extreme region here, we mean the area to either the left or the right of the test statistic. If our test statistic is negative, then the extreme region is to the left. If the test statistic is positive, then the extreme region is to the right. Now this p-value is calculated in this way because of the form of the alternative hypothesis. The inequality was not equal to, and so we have this type of p-value. So our extreme regions to the left, we find that area from our table A2, 0.0091, and then we take that times 2 to get our p-value. So our p-value is 0.0182. This type of test is called a two-tailed test because we have to take the area under one tail times 2. Okay. Now interpret it, we'll use the same criteria. We'll use a confidence level here of 99%, so alpha is 0.01. Our p-value of 0.0182 is just a little bit bigger than alpha, and so we do not reject the null hypothesis. We word it in the same way. The original claim does contain equality, so we're going to go to the right along the green arrow. Do you reject it? No, we do not. So we go down the red arrow. there is not sufficient evidence to warrant rejection of the claim that 10% of M&Ms are blue. That's our final conclusion. Okay. That may be a little bit surprising because our sample data seem to contradict the claim, but that contradiction, that level of contradiction, was not strong enough for us to indeed reject the claim. Okay. Well, now let's make a quick observation. We arbitrarily chose a 99% confidence level. Suppose we had chosen a 95% confidence level. So alpha is 0.05. Now that doesn't change our p-value. It's still 0.0182, but in this case that's less than alpha. So we get the opposite technical conclusion. In this case we reject the null hypothesis. So now when we word it, the original claim does contain equality. Go to the right. Do you reject it? Yes, we do. So there is sufficient evidence to warrant rejection of the claim that 10% of M&Ms are blue. So in this case, we got the exact opposite conclusion. At the 99% confidence level, we did not reject it. At the 95% confidence level, we did reject it. So the point here is that the confidence level can affect the final conclusion. Not always, but it can. So to quickly summarize here, the type of test that we have all depends on the inequality that appears in the alternative hypothesis. If our alternative hypothesis has a less than sign, then it's a left-tailed test. The p-value is the area to the left of the z-score. If our alternative hypothesis has a greater than sign, then it's a right-tailed test, and the p-value is the area to the right of the z-score. If our alternative hypothesis has a not equal to sign, then it's a two-tailed test, and the p-value is twice the area of the extreme region bounded by the z-score. Our criteria for coming to the technical conclusion is the same in every case. We reject the null hypothesis if the p-value is less than alpha. We do not reject it if p-value is greater than alpha. And then again, this is our technical conclusion, is that we either reject the null hypothesis or we do not. It's the only two possibilities for the technical conclusion. Okay. Then when we state our final conclusion, we want to do it in non-technical terms. We never want to use the term null hypothesis because a layman who doesn't know as much about statistics as us wouldn't know what we're talking about. Okay. And important point here, we never prove or disprove anything. We never ever use the word prove or disprove when stating conclusions of a statistical analysis. We maybe strongly support something or we strongly contradict something, but we never prove or disprove anything. So that's it for this lesson. The Course Compass homework is titled Section 8.